before I get into this, I think it's very helpful to understand a little bit about the history of the field, which is quite interesting. So I'm going to take you back in time to World War II. Probably the first real practical applications of computers was to help soldiers during World War II to aim their weapons at distant targets. This required compiling what were called ballistics tables. The soldiers would look up on the tables how to aim to get a certain distance, and that would help them to do their job better. Now, previously, before the computers that were developed in the 1940s for this purpose, the task required a lot of painstaking work by humans to create, they were called calculators, by the way. It was a profession. It wasn't a little thing, it was a profession. And the new electronic computers that were built back then, they could do in 15 minutes what it took a human calculator to do in 20 hours. Today, of course, that's about 1 millisecond, actually less than that. Put that in perspective. And after the war, they had built all this investment in these new kinds of machines. And the question they asked, of course, was, well, what else can we do with these fancy new machines? We can do ballistics tables and other calculations. What else could we do that would be good peacetime uses for this kind of technology? And around 1950 or so, an answer emerged. And that was that the answer was what we call today data processing. Many companies, such as IBM in the United States, saw a market for data processing machines that would be productivity aids that could replace all the legions of people and clerks that were powering the corporate offices and the government offices, processing data and doing paperwork. So now we're up to the part where artificial intelligence emerged as a discipline. The question was, if computers could crunch numbers for ballistics tables, and if they could process data for doing billing and things like that, why couldn't they perform other kinds of cognitive tasks? That was the question that was asked. So in 1956, I was 4 years old, so I was around back then. I didn't know about this. At Dartmouth College in the US, there was a summer session titled the Dartmouth Summer Research Project on Artificial Intelligence. And that was the first use of the term artificial intelligence. So they laid out the goal for that summer conference. There it is. That's a picture of the actual document. They laid out the goal of the enterprise by saying, the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can be in principle so precisely described that a machine can be made to simulate it. And they said for the conference, an attempt will be made to find out how to make machines use language, form abstractions and concepts, solve the kinds of problems that are now reserved for humans, and also to improve themselves. Now, I love to point this out on the slide. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists works on it together for a summer. They thought that would be adequate to solve these problems. Now, nothing much came out of that conference. In fact, they never actually even published a final report. But one important thing that did occur, and that is that the group that met that summer came together over a very particular approach to how to solve this problem. There's a fellow that I actually knew, I met when I was a student like most of you, called John McCarthy, that was the fellow who called this conference. And his specialty was mathematical logic. John McCarthy, he was a mathematician. And he believed that logical inference was the key to human intelligence. He thought that's what it was. It was our ability to do logical inference. Now, his approach later came to be known as the physical symbol systems hypothesis. And that was the dominant paradigm in artificial intelligence for at least the first 30 years or so after this Dartmouth conference. When I studied AI, that's what we studied, and that's what we learned. Now, the approach has many practical applications, and it's used today, even in use today. For example, for giving driving directions. When you do that on your phone, that's using these kinds of logical approaches. It's used for laying out warehouses and factories. And importantly, it's used to prove that complex computer chips meet their specification. That all uses this logical approach. But what happened was, despite decades of work, certain problems that were identified in that original 1956 conference proved very difficult to solve. And these included speech understanding and translation between languages and computer vision, just to name a few of those areas. Very little progress was made over the next 30 years on those problems. Now, what those problems had in common was that they required the interpretation of some very messy and unstructured real-world data, messy and unstructured in the statistical sense, such as recorded sound or pictures, digitized images. So meanwhile, while this was all going on, it turns out that there was another approach which existed back at that time. And as they say in English, a spoiler alert, that approach is what has now become machine learning. And how many of you are taking the machine learning course? Oh, you're all over, most of them over here, okay. This is like the Senate. We've got the conservatives over here and the liberals over there. Okay. Now, let me tell you a little bit about the history of this. It actually started around the same time as John McCarthy, in the late 1950s, with the work of a fellow by the name of Frank Rosenblatt, who was at a university called Cornell University. This is a picture of Professor Rosenblatt. I love this picture because he looks like he's 12 years old. Now, Rosenblatt, he was a professional rival of John McCarthy. And he thought that the class of problems that I just mentioned might be better addressed by writing simple feature recognizers in software. And he called these perceptrons. That was his branding, his name for it. And he organized these feature recognizers, or I'll call them nodes, into a series of layers. So nodes in higher layers were supposed to look for patterns in the output of nodes in the lower layers. And that's what we call today the neural networking approach, or deep learning approach, to artificial intelligence. And this was the original root of this. The technique was given the somewhat grandiose name of neural networking because it drew its inspiration from how they thought neurons in the brain might be organized. And actually, the history of that goes back even earlier to some work that was done at the University of Chicago. Okay, so what is machine learning? What is it really? Basically, machine learning is a collection of software techniques for extracting useful patterns out of very, very large collections of data. It turns out that if the collection of data is large enough, you can find some very interesting and subtle patterns in that data. Then you can take and classify those patterns in order to predict or to classify new examples of data that is presented to the system. In other words, you apply what you learned to a specific example and that you haven't seen before. And that's basically what machine learning is about. For example, machine learning programs are used to recognize objects in images, as you probably know, such as cats or dogs. Or they can find correlations between just about anything and stock prices, which is used to trade securities, people trying to make money in the stock market. So I want to briefly highlight the main differences between the symbolic systems approach for those 30 years and the new machine learning approach, which I guess has been 20 or 30 years now. The symbolic systems approach saw inference and reasoning as the hallmarks of human intelligence. And so they viewed that as a promising approach to solving the problem of making an intelligent machine. That's why they, early on, in the work that I did when I was a student, focused on problems that required a lot of thought, like playing chess or proving a mathematical theorem. Those are examples of the kinds of problems we worried about. Now, by contrast, machine learning regards, the machine learning school of thought regards perception and real-world engagement as the measure of some kind of success. And that's why they focus on tasks like speech recognition and vision and autonomous driving, blocking spam from your email folder, preventing credit card fraud. Those are the kinds of problems that these techniques are used for. So now you know that what both symbolic systems and machine learning are. But it raises a very interesting question. Why was one of these dominant for 30 years? And then everything flipped around. And the other approach is now dominant. Because when we talk about artificial intelligence today, almost everybody's talking about what is really machine learning, convolutional neural networks, and all the things that you guys are probably studying in your courses. Now, the short answer to that question is that the available technology, the computers and the storage and the networks and the data, have changed. Now, they didn't just change a little bit. They didn't really even change by a lot, but by a ridiculously large amount. And that changed what was possible. So if you look back over the past 30 years, computers have just about doubled in speed every 12 to 18 months. That may not sound like a lot, but that over 30 years, they've doubled 20 times. And that is a factor of, can anybody tell me? No, not too quick for you, huh? You weren't expecting me to ask a question. Okay, somebody over here is going. It's a factor of 1 million. If you double things 20 times, you get 1 million. Now, it's hard to come up with, that's my 1 million slide, getting behind. It's hard to come up with intuitive explanations for just how dramatic that difference is. I try to do this for my students at Stanford. But 1 million is literally twice the difference between the speed of a snail crawling across the ground and the speed of the space shuttle when it is in orbit around the Earth. That's only 500,000. So we're talking about twice something like that. Now, I'm wearing an Apple Watch right now. And my Apple Watch likely has more computing power than was available to the entire United States space program when it first put a person on the moon. So you think about that. Imagine, okay, we're going to put a man on the moon. All you have is this watch to run all your computations on. That's what they had. Now, I'm sure I don't have to explain the equally dramatic increase in the volume and availability of digital data. Now, at some point, that kind of difference in quantity becomes a qualitative difference. For all practical purposes, we're using different computer technology today than we were using 30 or 40 years ago. Because you don't race a snail the same way you race a spaceship. It's completely different. So let me come back to my slide here and say that the advantage of the symbol systems approach was that it could do a lot with very, very little data. A few simple facts, you feed it in, it would chug away, and it would reach some kind of useful conclusion. And that was a good match for the technology that we had 20 or 30 years ago. Now, by contrast, 30 years ago, machine learning suffered from a complete lack of data. to learn from. It was very hard. You guys weren't around to see this. You had to punch up cards, and you know, it's hard to imagine how little data you could get into a computer at the time. Even if you could get your hands on the data, the memory was very limited, and that limited what you could do. So the symbolic systems approach was dominant for the first 30 years, and relatively little attention was therefore paid to the machine learning approach. But as time went by, the situation reversed, and machine learning can now deal with these messy real-world problems as long as it has access to enough data. Now, the more data, the better the results you're going to get. So machine learning is a very good match to today's technologies and today's computers in our highly networked and data-intensive world. And that brings me to the present.